In the first chapter, we have seen an example of an arbitrage strategy, and one key component of that strategy was a risk-free asset. Therefore, in chapter 2, we want to spend some time talking about risk-free interest rates. And then we are also going to look at a derivative contract written on interest rates, and these are forward rate agreements. To start, I first want to talk about what are actually risk-free assets in the real world. In particular, there are different types of contracts which can specify as risk-free assets. And I want to start the discussion by looking at treasury rates. Treasury rates are interest rates paid by government for borrowing money. Note that borrowing by some emerging countries, like for example Argentina, is definitely not risk-free, since Argentina defaulted actually from time to time. However, if you consider some developed economies, like for example the UK, Switzerland, the US, Japan, the history shows that they are pretty reliable, and typically they do pay interest rates, and they do also repay the principal on the maturity date of their contracts. Now, just to look at the US, since US treasuries are probably the biggest market for government borrowing, we have treasury bills, which are short-term contracts. These are zero coupon bonds, meaning that from the time where the government borrows money until to the maturity date, they don't pay any interest, but they just pay the principal plus the interest just at the very end of the contract. And these contracts typically have a maturity between 4 weeks up to 1 year, and the government is typically borrowing on a weekly basis, so every week you have new of these treasury bills issued. Then we have treasury notes, which are more intermediate length contracts, and these maturities, they range between 2 years up to 10 years. Now, for treasury notes, these are actually coupon bonds, meaning that they pay interest payments in between since the government started borrowing and the maturity date. And these coupon payments, or these interest payments, are made every 6 months for treasury notes. And then we have treasury bonds. These are also coupon paying bonds, meaning again they pay interest during the lifetime of the contract, and again for treasury bonds they pay interest every 6 months, and the maturity of treasury bonds is longer than treasury notes, and these are between 20 and 30 years. Now, one issue with treasury bills, notes and bonds is always inflation. So they may be risk-free in terms of nominal interest rates, but they may not be risk-free in terms of the real value of money. Because it could be that after a few years, inflation is going to be very high, and in real terms, the treasury is not going to be worth much anymore. To counter that shortcoming, the US also issued treasury inflation protected securities, or short known as TIPS, and these securities always adjust the principal by the current consumer price index, the CPI. So this takes care of the fact that if there is very high inflation, then basically the government promise you to pay back more in the future, and they're also going to pay you interest on this higher principal. So in that sense, these TIPS can really be considered as risk-free in real terms, while treasury bills, notes and bonds, they are really risk-free just in nominal terms. Notice that the TIPS are not as widely available as treasury bills, notes and bonds. Maturities range between 5 and 30 years, and the liquidity of these contracts is not as high, meaning not so many people invest in TIPS, and TIPS are also not as highly traded as treasury bills, notes and bonds. There are two shortcomings of using treasury rates as risk-free interest rates. The first shortcoming is that even though you can invest in treasury rates and earn these interest rates, it may be very difficult to actually borrow at a treasury rate. So many market participants probably face much higher interest rates than treasury rates when they borrow money. The second shortcoming is due to bank capital requirements. Banks are required to hold a certain percentage of their balance sheet in safe assets, and these are typically treasuries. And so if banks are required to hold a lot of money in treasuries, this means that demand for treasury securities is pushed up, which means that prices for treasury securities are higher and therefore treasury rates are lower than what you would have if there are no capital requirements. Therefore, there is this hypothesis that treasury rates are somewhat too low or lower than the actual risk-free interest rate in an economy. The next example I want to look at are federal fund rates. In the US, banks are required to deposit some money with the Federal Reserve Bank. The problem with these deposits is that typically the Fed pays a lower interest rate to banks on these deposits than what banks can earn otherwise. Therefore, banks want to hold a minimum amount of these deposits at the Federal Reserve Bank. Now, for a bank during a specific day, they may trade and their balance sheet may temporarily grow, and therefore they are required to hold more of these deposits. Now, instead of the bank transferring some additional money to the Federal Reserve Bank, they may be able to find another bank who already holds some deposits at the Fed and whose balance sheet maybe has temporarily shrank a little bit during the day. And the bank who needs more deposits can then ask the other bank who has some excess deposits to borrow some of these excess deposits for one day. Now, the bank which borrows for one day the deposits from another bank will have to pay some interest, and that interest payment is the federal funds rate. So therefore, these federal funds rates are always just overnight, so for one day, and typically they are uncollateralized. However, they are not very risky because we are talking here about very big banks, and for one day it should be pretty predictable that these banks are not going to go bankrupt. Although the federal funds rate is pretty much risk-free, one problem of it is that the Federal Reserve Bank tries to steer the federal funds rate through its monetary policy. In addition to the federal funds rate, we have something called the discount rate. And the discount rate is the rate which a bank pays if it borrows directly from the Fed instead of borrowing deposits from another bank. The discount rate is typically higher than the federal funds rate. However, there are some circumstances where the discount rate was lower and where the Federal Reserve Bank was lending money at a relatively cheap rate to banks. These instances were typically during financial crises, like for example in the crisis of 2007, 8, and 9. The next example I want to look at is the repo rate. The repo rate is the interest rate for repurchase agreements. In a repurchase agreement, you're not technically borrowing money, but you're actually selling a security which you have to another party, and then you sign a contract that you buy it back at a higher price. In that sense, it is really kind of like borrowing money and paying that money back plus some interest and posting some collateral to make sure that you're not defaulting. But it is actually even better than a collateralized loan. Because if, let's say, I am borrowing money and I go bankrupt, then the party which was lending me money with just normal collateralized debt, they would have to wait through the entire bankruptcy procedure to then actually be able to seize the collateral. However, with a repurchase agreement, since they bought that asset from you, if you go bankrupt, they already have that asset in their hand. So they don't actually have to claim the collateral anymore. They already have it. In that sense, repurchase agreements are pretty much risk-free. Now, for repurchase agreements, these contracts are typically just overnight. So again, these are interest rates just for one day. Finally, the London Interbank Offered Rate, or LIBOR, is the interest rate at which large banks borrow from or lend to each other. Therefore, the LIBOR can also be considered as the funding costs of large banks. The LIBOR is also used as a reference interest rates for many different transactions. For example, the LIBOR is used in syndicated loans, where multiple banks together lend money to a large corporation, and so as an interest rate for these syndicated loans, they would use the LIBOR plus a certain margin on top of that. Moreover, the LIBOR is often used for mortgages, and the mortgage interest rate would be equal to the LIBOR and a margin on top of that. Derivative contracts also often link their payoffs to the LIBOR interest rate. The LIBOR rate is also commonly used as a risk-free interest rate to price derivatives. The LIBOR is set daily by the Intercontinental Exchange, or ICE, and I also provide a website to the ICE for more information about the LIBOR. Notice that before 2014 the LIBOR was set by the British Bankers Association. Even though the LIBOR has the word London in its name, it does not only apply for the British pound. The LIBOR is available in US dollars, euro, British pounds, Japanese yen, and Swiss francs. Moreover, the LIBOR has multiple different maturities. So the shortest term LIBOR is just overnight. There is a 1 week maturity, there's a 1 month, 2 months, 3 months, 6 months, 9 months, and 12 month maturities. Notice that there are a few shortcomings of the LIBOR. First of all, the LIBOR is determined by estimates which are provided by large banks. So basically every day large banks would submit quotes which indicate what are the funding costs which they face in all these different currencies to borrow money at the various different maturity days. Then the Intercontinental Exchange would aggregate all these submitted quotes by the large banks and set the LIBOR. One problem of this is that the LIBOR doesn't necessarily reflect true transactions, but it's really just a self-reported rate. And this was really one of the reasons why there was a scandal in 2012 where some big banks started to manipulate the LIBOR. Second, the LIBOR is not quite risk-free because from time to time large banks can actually default. So for example, Lehman Brothers, which was one of the very large financial institutions, and considered to be very comparable to Goldman Sachs, went bankrupt in 2008. For these reasons, the LIBOR might be not the best rate to be considered as a risk-free interest rate, and therefore maybe we shouldn't use it to price derivative contracts. Now notice that after the LIBOR scandal, regulators also intended to discontinue the LIBOR, and they set a date until end of 2021. And they are actually looking for suitable replacement rates. As of today, the suggested replacement rates are overnight rates. So again, meaning interest rates applying just for one-day lending. In the US, we have the secured overnight financing rate, or also known as SOFR, and that is an interest rate based on repurchase agreements and therefore is actually secured lending. In contrast, in the UK, the regulator considers the Sterling Overnight Indexed Average, or also known as SONIA. SONIA is actually unsecured lending, and therefore it's quite different from the SOFR. In the Eurozone, regulators push for the Euro Overnight Indexed Average, or EONIA, and in Hong Kong, the Hong Kong Overnight Indexed Average, or HONIA, is considered. The EONIA and HONIA are very similar to the SONIA, and they are also unsecured lending. Notice that all these rates are only valid for overnight lending, so just for one day. Now, how can you get a risk-free rate for a longer maturity? Well, people suggest that we can use overnight index swap rates. So in an overnight index swap contract, one party would agree to pay on a daily basis always the overnight rate. So for example, the SOFR in US dollar or the SONIA in British pounds. And the counterparty would pay over a certain time horizon until the expiration of that swap a fixed interest rate. And so the overnight indexed swap rate, that's that fixed interest rate in that swap contract. To illustrate why swap rates are useful risk-free interest rate, let me draw this on the virtual whiteboard over here. Let's consider party A who would like to lend $100 million for 1 year time. What they can do is they can go to party B and just lend this $100 million for 1 year. In return, B will promise to return the $100 million plus interest. Now the problem of this is if you lend for an entire year, there is a chance that B goes bankrupt and you never recover the $100 million and the interest. Now instead what A can do is they can lend the $100 million instead of for 1 year, just for 1 day to the healthiest bank which they see in the market. And in return, the healthiest bank returns the $100 million plus interest after 1 day. This way, A can be sure to always recover the 100 million, because if you on a daily basis always pick the healthiest bank, well, then there is almost no way that this bank is going to go bankrupt just after one day. The problem here, however, is that this daily interest rate will fluctuate. So sometimes Bank A will receive a high interest, sometimes a low interest. Now, what can A do? A can turn to the swap market, and they can sign a contract with a counterparty where A delivers the daily interest rate and the counterparty pays a fixed interest rate based on the $100 million. Now, if you look at this combined position for A, again, they lend $100 million once a day, receive again the $100 million after one day plus the daily interest rate, and they take this daily interest rate, deliver it to the counterparty, and in return get a fixed interest rate. And this swap contract is signed for an entire year, while this lending is always just on a daily basis. So what is the risk over here? Well, again, since you lend to the healthiest bank, you basically are guaranteed that you always receive your $100 million back. Now, there is still some counterparty risk in that swap contract, because it could be that that counterparty in the swap will default. But what is at stake here? Well, it's just that exchange between interest rates, which is just a very small percentage, or even less than 1% of that $100 million. However, if I would lend for the entire year to party B, I could actually lose the entire $100 million. So therefore, that lending on a daily basis and converting the daily interest into a fixed interest rate for a whole year, that is much safer, because for sure I never lose my $100 million. So therefore, we can consider overnight index swap rates, so which are these fixed interest rates in the swap contract, as risk-free interest rates, which market participants can actually earn in the market. So from now on, I'm only going to refer to the risk-free asset or the risk-free interest rate, and I'm not going to bother about which interest rate this is going to refer to in the real world. The first thing which I want to do is I want to talk about compounding frequency, which is really the main measurement unit of interest rates. The compounding frequency in particular determines how much return you actually earn over 1 year time investment. And this return over this 1 year time we also refer to as the effective annual interest rate or the annual equivalent rate. To illustrate the idea of compounding, I want to turn to the virtual whiteboard again, and I would like to look at a specific example where we look at an annual interest rate R equal to 10%. And so what I want to look at is first at a 1 year time horizon. So we have small t equal to 0, and then we invest until time capital T equals to 1 year. Now, if I tell you you can earn interest rate R equal to 10%, and if you have 1 times compounding per year, so CPA stands for compounding per annum, then $1 will just earn interest at the end of the first year. And so you're going to end up with this initially invested $1 multiplied by 1.1, referring to that 10% annual interest, and that gives you $1.1. Now, if you would change the compounding frequency to 2 times compounding per annum, then this $1 will earn interest after 6 months. And in particular, it will earn half of the 10%, so 5% interest. So I have my $1 initially invested multiplied by 1.05, or this is equal to $1.05 after 6 months. Now over the second 6 months, I will earn again 5% interest, but now I don't earn it just on $1, but I earn it on this $1.05. So I multiply this entire amount by 1.05. So this then yields $1.05 to the power of 2, or this is also $1.1025. So we see now that because we have 2 times compounding per year, we earn interest on interest, and therefore we earn a little bit more money after than 1 year. So we can now also look at an example of 3 times compounding per annum. And in this case, $1 invested at the initial point in time earns over the first 4 months 1/3 of 10%. So I have $1 plus 10% over 3. And then I can invest that entire amount for another 4 months. And on that invested money, I will earn again 10% divided by 3. Or in total, I have now this 1 plus the 10% divided by 3 to the power of 2. And then over the last 4 months again, on this entire amount, I will earn again 10% divided by 3 interest on the entire amount. And therefore, I end up with 1 plus 10% divided by 3 to the power of 3. Now we can of course generalize that for m times compounding per annum for any integer m. So again, we would start with $1, then we take the first time step. After that, we have our initial $1 plus the annual interest rate R divided by M, and then we reinvest it again on that entire amount. I will earn again an interest equal to this annualized rate R divided by M, or again, as before, that will be 1 plus annualized interest rate divided by M to the power of 2. And then we can keep going m times like that. And at the final date, what we're going to end up with is just the initial dollar plus the annualized interest rate R divided by M to the power of M. So that's the general formula for m times compounding per annum. So $1 grows to 1 plus annual interest rate divided by how many times you compound per year to the power of how many times you compound per year. Now we can also look at the limit where m goes towards infinity, meaning that you make each time step here very, very tiny. So you keep earning interest basically on a continuous basis, and that's why we also call this continuous compounding. So we have that $1. We take very, very tiny time steps going forward until after 1 year. If I take the limit, I can rewrite this as e to the power of the annualized interest rate R. And e over here, that is Euler's constant, and that is equal to 2.71a and so forth. And this gives us the second important formula here, which is again continuous compounded interest where $1 grows after 1 year to e to the power of annualized interest rate number of dollars. Now this is the interest which you earn for 1 year. Now what happens if we want to look at multiple years? So we would start again at time t equals to 0 and we look at 3 years. And here in between is 1 year and 2 years. Okay, so if you had again 1 time compounding per annum, then we know that $1 invested at 10% will grow to $1.1. And then, well, if you would invest it again for 1 more year, then you had that $1.1 multiplied by 1.1, so the 10% interest, which gives you $1.1 squared. And then if you invest that again, that will give you this $1.1 squared, again multiplied by 1.1 or $1.1 to the power of 3. And similar for m times compounding, you start with $1. This grows, as we have seen before, to 1 plus the annual interest rate divided by m to the power of m dollars. And now after the second year, simply what you do, you take again this dollar amount which you had after 1 year and you multiply that again by how much you earn over 1 more year. So just taking again, multiply by 1 plus r divided by m to the power of m, and you see immediately that's just this entire thing to the power of 2. So 1 plus annualized interest rate divided by m to the power of m multiplied by 2. And equivalently, if you invest for 1 more year, all you would have to do is you have to change the exponent, where you have now 1 plus annualized interest rate divided by m to the power of m, which is for 1 year, and now I just multiply that m by 3 to invest for 3 years. And similar for continuous compounding, we had $1 grows after 1 year to e to the power of r dollars. Now, if I reinvest that, then I have again, after 1 year, I had e to the power of r dollars. And then for 1 more year, I will multiply that again by e to the power of r, which then is just e to the power of r multiplied by 2. And again, if you would invest this entire amount for 1 more year, then after 3 years, you would have e to the power of r multiplied now by 3 years. And so more generally, we can also write for an investment from time small t, which doesn't necessarily have to be 0 anymore now, to someday capital T in the future. And that difference, capital T minus small t, that could be, for example, again, 3 years, it could be 10 years, but it also could be less than a year. So for example, it could be 4 months. In that case, capital T minus small t would be 4 divided by 12. Now, so in this general case, if you have m times compounding per annum, then $1 will grow to 1 plus annualized interest rate r divided by m to the power of m. That would be the interest for 1 year. And now I just multiply that m by the time length in number of years, corresponding to what we just did above. And similar for continuous compounding, if you start with $1, if you invest that, well, then we know per year you would earn e to the power of r dollars. And now all I'm doing is I multiply that r by the number of years for which I invest. If you look again at the slides, we have here again this formula of an investment over 1 year for m times compounding. Now I subtract here -1, that just subtracts that initial dollar, and therefore we have here the rate of return. And similar over here, we did that adjustment for general time horizon, capital T minus small t, number of years. And again, the -1 is just subtracting that initial dollar which is invested, and therefore this gives us the rate of return over that time horizon, capital T minus small t. And here we have the corresponding formula for continuous compounding. Now we can also work out the relationship between a continuously compounded rate and an equivalent rate in m times compounding. Here the idea is just try to figure out if I have, for example, a 10% rate in m times compounding, let's say it's quarterly compounding, where m is 4, then how big would a continuously compounded rate RC have to be such that I earn effectively the same amount of interest over 1 year time? So the way you would do it, you would want to just equalize these two formulas over here, where you plug in for your m times compounded interest rate, and then you want to figure out, well, what type of continuously compounded interest rate do I need such that these two amounts are going to be the same. Okay, and that's going to be this formula over here. If I have some m times compounded rate, that will give me the continuously compounded rate, which effectively earns me the same amount of money over 1 year in investment. And over here, this is just the reverse, where I solve that equation for Rm. So this tells me if I have a continuously compounded rate, then how big does a m times compounded rate have to be such that I earn the same amount over 1 year. Notice that the continuously compounded rate will always be somewhat smaller than the m times compounded rate, such that they are equivalent. The reason is, well, with continuously compounding, you get more interest on interest, and therefore this annualized interest rate can be smaller to afterwards still yield the same amount of return. Here in this slide, I just have again these examples as what I wrote on the virtual whiteboard. I have an annualized rate of 10%. If you only have 1 times compounding, so meaning you only get interest at the end of the year, then over 1 year, the effective interest rate which you earn is 10%. If you get interest on interest after every 6 months, well, then you get slightly more effective return after 1 year. It's 10% plus another 1/4%. And you see, the more I get interest on interest, the more compounding I have, until to continuously compounding, where you get most interest on interest, this will actually grow to 10.5%. Now, if you go to a bank and you say you want to invest money for 1 year, they may give you a very different interest rate than if you commit to invest for 2 years or 3 years or a much longer time horizon. And so for each maturity, for each investment horizon, we have a different interest rate. and we also call these the spot rates. I'm going to indicate them in our lecture by R for that interest or that spot rate, and by the subscript small t, that's when you start investing, comma, the subscript capital T, the time until when you invest. So the time horizon is just going to be capital T minus small t, number of years. Notice that these spot rates, we typically list them in annualized terms so that we can use the previous equations, and they are then also more comparable across different maturities or investment horizons. Here in this table, I'm going to give you just one numerical example. Of course, in the market, rates may look very different. RT over here, that's just for an instantaneous investment, so for a very tiny time horizon where basically capital T and small t are almost the same point in time. Let's suppose the bank would pay you per year 2.5%. And then let's say you go to the bank and you say, well, I want to invest longer than just a very small time horizon. I want to commit that I invest for 6 months. Then the bank would say, well, then we give you the spot rate where you earn 4% per year for that 6-month horizon. And if you invest for an entire year, then we're going to promise you even 5%. And then the bank says, well, the longer you commit that you leave the money with us, the higher we're going to give you an interest rate. And so here we would see that if I invest up to 30 years, but that means I cannot withdraw the money anytime before that, then they will be willing to pay me even 6.5% per year. Now we can also plot that where we look at the horizontal axis, that's the investment horizon or that maturity, that's the capital T minus small t. And on the vertical axis, we look at the percentage spot rate. Then if we plot this is all these different spot rates from the table. This we also call the term structure of interest rates or the yield curve. Now next I want to turn to pricing bonds. And a bond contract is basically a promise that you receive at some future points in time. Here I list them as T1, T2, up to Tn. You receive a specific cash flow CI. Okay, so let me just draw that on the timeline on my virtual whiteboard. So you start at time t0, you can also set this equal to t, and for that timeline, the maturity date, capital T, or we also can call this Tn. We have certain times, let's call it t1, and then maybe t2 over here. And notice that it doesn't have to be equally spaced, although for bonds most of the time it is. And then there might be many more dates in between. And each of these dates, you are promised a certain cash flow. So at T1, you get cash flow C1. At time T2, you get cash flow C2. And then you get some other cash flows in between. And the final cash flow would be Cn. Okay, so that's corresponding to what I described in this first bullet point. Now, if you want to find the current price, let's denote it by P with that time index 0. So with 0 over here, what we would assume is that T0 is equal to 0. If you want to find that price P0, how do you do that? Well, basically what we want to do is we want to just sum up the present value of all the cash flows which we receive in the future. Let's do that. So for the first cash flow, I use C1 and I discount that by the spot rate between time 0, that's the initial date, and time T1. And that's the annualized rate, so I still have to multiply that by the time length between time T1 and T0, which is 0. And then I would add to that the second cash flow, which I receive at time T2. And this second cash flow, I have to discount by a different discount rate. Here I use the spot rate R from time 0 to time T2. And again, this is annualized discount rate, so I have to multiply that by T2 minus 0. And so I add up all these discounted cash flows until to the final cash flow Cn, and I multiply this one by the spot rate, which applies between time T0 or time 0 and time Tn. Again, multiplied by the length of that time horizon, which is Tn minus 0. Now you can compare this formula with what I have here in the lecture note. And that's exactly the specification over here, where I use these continuously compounded spot rates. Now you can also write the same thing for M times compounded spot rates. Well, then you just have a different discount formula. Again, $1 grows to 1 plus that annualized rate divided by M to the power of M times the number of years. And so discounting means you just divide your cash flow by this gross return. Now, the last thing to mention is a zero coupon bond. In a zero coupon bond, all these cash flows here are zero, and you only receive one final cash flow at the maturity date. And we also typically call this the face value of the bond and denote it by F. Coupon bonds, these are bonds which pay payments between the initial date and the maturity date. And typically for coupon bonds, these time steps here, they are equally spaced when you receive coupon payments, and the actual coupon payments are always going to be the same size. And in particular, we set these coupon payments equal to what we call the coupon rate. That's a percentage of the face value which you receive per year. And if you have n coupon payments per year, then we will take that coupon rate divided by n times the face value. That's the coupon which you get at each point in time. Now, how do you value the bond? Well, we use exactly the formula from before, where we now just replace the CI and the specific points TI by equally spacing them, and that's going to give you these formulas here, one for continuous compounding and one for M times compounding per year. Okay, so again, this thing over here, that's the annualized coupon rate of the bond, n coupons per year, and you get that percentage of the face value of the bond. So that's the coupon which you get at each point in time, and you just discount that by the appropriate spot rate between time 0 and the time when you receive it, so T divided by N, and you multiply by that investment horizon between time 0 and time T over N. The last thing to know is that when the present value of all these coupon payments, or that value of the bond at time 0, when that is exactly equal to the face value of the bond, then we say this coupon bond is traded at par. Let's look at some examples, and for these examples I'm going to use that example term structure which I had on the previous slide. So going back, are these rates which I'm going to use for the example. So first I want to price zero coupon bonds. What is the current market price at time 0 of a zero coupon bond with maturity in half year? I'm going to write that over here, the price of a bond at time 0 with maturity date after 6 months. And let's say the face value is $1,000. Well, then I'm going to take these $1,000 which I get after 6 months, and I discount them by the 6-month spot rate. Okay, so go back to that table. 6-month spot rate, we say, is in continuously compounding 4%. So I plug that in over here. E to the power of minus is 4% per year, and I multiply that by 6 months. So that's going to give me the present value of this $1,000, and that's $980. So that's the value of the zero coupon bond at time 0. How about a 1-year zero coupon bond, again with face value of $1,000? So the 1-year zero coupon bond says you receive $1,000 after 1 year. Now I discount this $1,000 by the 1-year spot rate, and let's go back to the table. The 1-year spot rate we have here is 5% continuously compounded. So that means I multiply the $1,000 by e to the power of minus 5% multiplied by 1 for 1 year. So I don't need to write that. And that gives me $951. For a 2-year zero coupon bond, again with face value $1,000, I do an equivalent thing. I say, okay, I get $1,000 after 2 years. Now I need to discount that by the 2-year spot rate. Again, go back to our example. 2-year spot rate is set at 5.5% per year. So what I do is I multiply the $1,000 by e to the power of minus 5.5% multiplied by 2 years. This gives me $896. Finally, the last example is a 3-month zero coupon bond with $1,000 face value. So here I get $1,000 after 3 years. Go back one more time to that table. 3-year spot rate is 5.9%. So that means that you take $1,000 times e to the power of minus 5.9%. That's per year. So I multiply that again by 3 for a 3-year time horizon, that gives you $838. Now we can also look at an example of pricing coupon bonds. Let's look at a 2% annual coupon bond with 3 years to maturity and face value of $1,000. So that means you get 2% of $1,000, which is $20 after the first year, after the second year, and in the third year you get the last coupon of $20, plus you get your face value of $1,000. So you get $1,020. So now how do I get the present value of that? So the first year coupon of $20 is discounted by the 1 year spot rate, so multiplied by e to the power of minus 5%, multiplied by 1 for 1 year. And then plus $20 coupon discounted by the 2 year spot rate for 2 years. So that means e to the power of minus 5.5%. That's the annual 2 year spot rate multiplied by 2 years. And then plus the final payment of the face value of $1,000 plus the final coupon of $20 multiplied by e to the power of minus the 3 year spot rate of 5.9% per year multiplied by 3 years. If you add all that up, that gives you $891. Now we can also look at an example of a 10% coupon bond with 3 years to maturity. That means you get 10% of $1,000, so the coupon payment is $100. And so you do the equivalent thing as before. You take the $100 discounted for 1 year by the 1 year spot rate. You take another $100, which you get after 2 years, discounted by the 2 year spot rate for 2 years. And then you take the final payment of $1,100, discount that by the 3 year spot rate for 3 years, add up everything, and the price of that bond is $1,106. Notice that in the market, you can always look up the yield curve from data providers as, for example, Bloomberg, or the US Treasury Department always posts a Treasury yield curve. However, where do they actually get the different spot rates or that yield curve from? Well, the way you do that is you look at all the bonds which are traded out there. You write down for each bond pricing equations as we did over here. And then you back out what do these spot rates have to be such that all these bonds are fairly priced. And we call this the bootstrap method. And in our problem sets, there's actually one example where I give you different traded bonds and I'll ask you to back out what are the different spot rates and then draw the yield curve. Now let's look at another concept of bonds, and that's the bond yield. The bond yield, which I denote by variable y, that's just a constant discount rate which discounts all the cash flows. So let's look again at the case of continuous compounding. So I denote that by YC for the continuously compounded bond yield. So for a bond with coupon payments CI at all points TI, what I do instead of discounting these coupon payments by the respective spot rates, instead I just discount each coupon payment by the same yield YC. So in that sense, I assume here that each coupon payment CI, even though they're made all at different points in time, is discounted by the same yield instead of always by corresponding spot rates, okay? And so this yield therefore gives me some type of average discount rate which applies for a specific bond. Notice that a yield is always specific to a bond. So it always depends on when you get coupon payments and how big these coupon payments are. The yield, of course, I can also write for m times compounding, and in that case I would just use a different type of discounting formula. Instead of using that e to the power of minus the discount rate times the time horizon, I would use 1 divided by 1 plus this m times compounded yield per annum divided by m to the power of m times the time horizon for which I need to discount. Okay? So the yield is in some sense just a weighted average of the spot rates in the markets. Well, because this formula at the end of the day also has to be equal to the formula which we had over here. Okay, so instead of using spot rates, I just use a constant yield, and therefore the yield has to be some weighted average over these spot rates. Okay, so in both cases, these formulas are equal to the market value of the bond P0, which is in both cases the same. Now, this weighted average is not very simple to get, and in general, you need quite sophisticated calculator which can solve a nonlinear equation. There are some very specific examples where it is easy to determine the yield, and this would be, for example, zero coupon bonds, because in zero coupon bonds you have only one coupon payment at the very end, and therefore you don't have an entire summation of terms, and you can very easily just take the initial price of the bond divided by that final coupon payment or by the face value, take the natural logarithm, apply it by -1 and divide it by the time horizon, and that immediately gives you the yield of the bond. And in particular, if you think about the zero coupon bond, and if you look at that formula, again, compare it to the formula over here, and if you only have one cash flow at the very end, well, then you see immediately that the yield of that zero coupon bond has to be exactly equal to the spot rate, which applies to the time horizon of that zero coupon bond. Notice that for a coupon bond which trades at par, the yield of the bond is always equal to the coupon rate of that bond. Notice we can apply this knowledge to floating rate bonds, and in particular floating rate bonds, they always pay the current interest rate. So meaning if you have a 1 month floating rate bond, then that bond would always pay on its principal or its current value, it would pay the 1 month interest rate or the 1 month spot rate. And therefore, the coupon rate of that bond, by definition, is always equal to the current spot rate, which is also equal to the current yield. And therefore, the floating rate bond is always traded at par. And we're going to use that knowledge also later in the chapter where we talk about swap contracts. Let's go back to our questions of the different types of bonds. Let's look at the 2% annual coupon bond with 3 years to maturity and a face value of $1,000. So we have established before where we used the different 1, 2, and 3 year spot rates to discount these different payments, that bond value is $891 today. So if you want to find the yield of that bond, then we say, well, if you get $20 after 1 year, you discount that. Now, not by the 1 year spot rate, but by the yield of that bond. Notice I denote it by Y, and then in the superscript I write it applies to the bond with 3 years maturity and 2% coupon rate. Then I discount the second coupon after 2 years, again by the same yield, but now by 2 years. And then the last payment of $1,020, I discount that again by the same yield Y, and just multiply it by 3 years. And again, now I say that this present value of these cash flows has to be equal to the current price of the bond, which again, I found from earlier discounting the cash flows by the corresponding spot rates. So I have here one equation with one unknown, that yield Y. But again, the problem is that this is a nonlinear equation, and so it's not very straightforward to solve that. So you need some calculator which can do some numerical optimization to back out what is this value Y. And so in particular, if I do that with a calculator, then I get Y is equal to 5.89%. Now I can do the same thing for my other 3 year coupon bond with 10% coupon payments. So here I just replace each coupon payment by $100. And again, now here, this bond is going to have a different Y. That's why I denote it by Y for the bond with 3 year maturity and the coupon rate of 10%. So this is a different value than what we had for the previous bond. Again, I do this for the first coupon payment, the second coupon payment, and the final payment of that bond. And I set all these present values where I discount by the yield of that bond equal to the value of the bond of $1,106. That's the value I found earlier by using the spot rates to discount these coupon payments of that bond. Now, if I solve this nonlinear equation for the bond yield Y, I get a yield of 5.85%. Notice that the yield of the 10% coupon bond is actually lower than the yield of the 2% coupon bond. Now, is this surprising? And maybe you want to stop the video at this point and think a little bit about why could it be that the 2% coupon bond has a higher bond yield than the 10% coupon bond? To explain this, I want to go back to my virtual whiteboard, and I want to draw this very quick. So in our case, our yield curve looks something like this. We have here the 1-year time horizon, 2-year time horizon, and 3-year time horizon, where again the spot rates are higher for longer investment horizons. And now if you think about the yield as a weighted average over these 1, 2, and 3-year spot rates, then let's try to figure out about how big should these weights be. And again, I told you, because it's a nonlinear equation, it's kind of hard to exactly determine the weights on the different spot rates, but we still can kind of get an intuitive sense of which spot rate should get a bigger weight compared to the others. And so if you think about the 2% coupon bond, you see that very small payments are made in year 1 and year 2, and most of the money is received in year 3. So if you think about that, the expression using the yield for discounting or the expression using the spot rates for discounting have to be the same, then most of the value of that bond is really just earned from that final payment. And therefore, the yield has to be very similar to the 3-year spot rate. And very little weight will be placed on the 1 and 2-year spot rates. So I can maybe draw that with some like bubbles around how big are these weights going to be on the 1-year and 2-year spot rates. Well, they're going to be very small, while the weight placed on the 3-year spot rate, if I determine the yield of that 2% coupon bond, will be very large. Now, if you compare the 10% coupon bonds to the 2% coupon bonds, then even though the payments in year 1 and year 2 are smaller than in year 3, in relative terms, the payment in the year 1 and year 2 is still bigger for the 10% bond than for the 2% bond. So drawing this in the figure over here, using blue color, I would draw relatively bigger circles on the 1 and 2-year spot rates and a relatively smaller circle on the 3-year spot rate. Now, it's still true that the payments in year 1 and year 2 are much smaller than the payment in year 3. So to determine the yield of the 10% coupon bond, I'm still going to draw the biggest circle or the biggest weight on the 3-year spot rate and smaller circles for the 1 and 2-year spot rates. However, in relative terms to the 2% bond, this blue circle is bigger than the red circles for year 1 and 2, but the blue circle is smaller than the red circle, so indicate the relative weight for the 10% bond is smaller in the 3rd year than for the 2% bond. Therefore, that means that the yield of the 10% bond is going to be relatively smaller because 1 and 2-year spot rates are smaller than the 3-year spot rate. And that's exactly what we see over here. The yield of the 10% coupon bond is a little bit smaller than the yield of the 2% coupon bond. Just to make sure that this argument is clear, let's try to draw a different picture. Now our yield curve, instead of upward sloping, is downward sloping. Now the 1-year spot rate is larger than the 2-year spot rate, and that's larger than the 3-year spot rate. Again, to determine the yield of the 2% coupon bond, you put very little weight on the 1-year and the 2-year spot rate, and you put a lot of weight on the 3-year spot rate. Now, in this case, it would tell you you get a relatively small yield. So the yield would be very similar to that relatively low 3-year spot rate. Now, in the case of the 10% bond, again, I put relatively bigger weights on the 1-year and 2-year spot rates and a relatively smaller weight on the 3-year spot rate. Now, it's still true, most of the weight is going to be on the 3-year spot rate, so the yield is still going to be relatively close to the 3-year spot rate, but in relative term to the 2% coupon bond, the yield now places bigger weights on the 1 and 2-year spot rates, and therefore the yield of the 10% coupon bond in this example will be relatively larger than the yield of the 2% coupon bond. So it depends on whether the yield curve is upward or downward sloping, whether the 10% coupon bond yield is higher or lower than the 2% coupon bond yield. Next thing I want to talk about is the duration of a bond. The duration measures how long on average you have to wait to recover your initial investment. And so therefore, the duration is some weighted average over the time horizons which you wait for all the different coupon payments. In particular, the duration of a bond is defined as the present value of each cash flow which you receive, so cash flow at time ti, discounted by the yield of that bond by ti years, so by the time horizon until you receive it, and then I divide that by the current value of the bond, so this gives me the percentage of the bond value which I receive at time ti. And this is going to be the weight which I place on the number of years I have to wait until I get that cash flow CI, indicated by TI number of years. And so the duration then just adds up all these different time horizons I have to wait, weighted by the relative value of the bond which I receive at these points TI. Again, I can write that both for a yield in continuous compounding or a yield in M times compounding per annum. Notice that the duration of a bond is large if the bond pays out most of its cash flows at the very end of the bond contract. And the duration, on the other hand, is relatively small if the bond pays out most of its cash flow already very early in time. Finally, the duration of a bond portfolio, so investing in several bonds at the same time, it's just going to be the weighted average of the durations of these different bonds, where the weights are determined by how much you invest in each bond out of the entire investment. So let's look again at our examples of the 2% and 10% annual coupon bonds. For the 2% annual coupon bond, we said you get $20 after the first year. I discount that by the 5.89% yield of that 2% coupon bond for 1 year. I divide it by the current value of the bond of $891. So this entire thing tells me what fraction of the bond value do I receive after 1 year. And I multiply that by 1 year, so I omit the 1 multiplication. Then I add to that the second coupon, which I get after 2 years, discounted by the bond yield, again of 5.89% for 2 years, divided by the current price of the bond. So again, this is the value of the bond which I receive after 2 years, and I multiply that by 2 years I have to wait to receive that cash flow. And then finally, I have the $1,020, that's the final payment in year 3, discounted for 3 years by the bond yield and divided by the current price of the bond. That again tells me what fraction of the bond value do I receive after 3 years, and I multiply that by 3 years to receive that payment. Adding up everything, I get a duration of 2.94. This is very close to 3 years because I really get very little cash flows in year 1 and year 2. I get most of my bond value just at that final date. In comparison, the 10% coupon bond, here I'm going to use 10% coupon or $100, which I get after 1 year. I discount that by the bond yield for the 10% coupon bond. That bond yield is 5.85%. Notice that again, a different value than for the 2% coupon bond. Divide that by the current price of the 10% coupon bond. So that gives me the fraction of the bond value which I receive after 1 year. I multiply that by 1 year, which I have to wait for that cash flow. Then I have the second coupon of $100, discount that by the 5.85% yield of that bond for 2 years, divided by the value of the bond. That gives me the current value of that bond, which I receive after 2 years. So I multiply that by 2 years, which I have to wait to receive that. And then finally, the $1,100 discounted for 3 years by the bond yield of 5.85%, divided by the current price of the bond. So that tells me after 3 years, this is the percentage of the bond value which I receive. Again, adding up everything, this is not too far from 3 years, again, because most of the money I just get at the very end. However, we notice that the bond duration is a little bit shorter than for the 2% bond, because again, in relative terms, with the 10% coupon bond, I get actually relatively more money already in year 1 and year 2. So a higher percentage of the bond value is paid out already in the year 1 and year 2 compared to the 2% bond, and therefore the duration of the 10% coupon bond is a little bit shorter than for the 2% coupon bond. Next, I want to talk about bond price volatility. Bond price volatility measures by how much does a bond price change if the yield of a bond changes. And the yield of a bond changes if there's some shock to interest rates and the term structure of interest rate changes. The bond price volatility is defined as the percentage change in the bond price as the yield changes. And the percentage change can also be written as the first derivative of the bond price with respect to the yield divided by the bond price. Okay, so this thing up here, that just tells me by how much does the bond price change if the yield changes a little bit. Now, if I have continuous compounding, I know that the bond price is the sum of the present values of all the cash flows. So where the present values are defined by discounting by the bond yield. Now what I can do is I can take the derivative with respect to the variable y, that bond yield, and that's actually quite simple to do for an exponential function. What I'm going to end up with is basically, again, this present value of each cash flow, and now it's just multiplied by minus ti, which is that part in the exponent where also y shows up. Now, if you look at this formula, well, that's actually exactly the same as the duration. Well, it's actually minus the formula of the duration. Okay, so in that sense, the bond price volatility, so this percentage change in the bond value, if the yield just changes a little bit, is exactly equal to minus the duration of the bond. To illustrate this, let me turn to the virtual whiteboard and let me illustrate how the price of a zero coupon bond depends on the level of the yield. So if the yield is relatively small, let's call it Y1, then there's not so much discounting of the face value and we're going to get a relatively high zero coupon bond price. However, if the yield is relatively high, well then there is much more discounting and the price of that zero coupon bond is now much lower. And if you look at many different possible values of the yield and draw all these bond prices of the zero coupon bond, then we're going to get a curve something like this. What is clear is that if the yield goes up, then the bond price drops, and therefore we can explain this negative sign over here. The second thing is about the duration. Longer duration basically means that this capital T for the zero coupon bond is much larger. Okay, so you get your final payoff much later in time. Now, if I increase capital T, that means the yield, the discounting, is multiplied by a larger number. And therefore also, if the yield now increases from Y1 to Y2, then that difference is going to be multiplied by a bigger number. And therefore, the price drop in that zero coupon bond is even bigger. This explains why, again, this percentage change in the bond price depends on the duration. The larger is the duration, the more the bond price is going to drop if the yield increases. Notice here I can also write the same formula for m times compounded bond yield. So here this bond price P0, depending on the yield, will be just the sum of the cash flows discounted by the m times compounded yield. Now if you take the derivative, things are slightly more complicated, but you still can do that actually quite easily. You're going to end up with this formula over here. If you look at this carefully, then you notice this is again equal to minus the duration, but then there is a second term due to this +1 in the exponent, and we call this modification of the duration, or this entire thing is also known as modified duration. So why do we have modified duration? Well, it just comes from math. If you take the first derivative of the bond price, if you have m times compounded yield, then you just don't end up with the duration, but also this division by 1 plus the yield divided by m. Note that these formulas only apply for infinitesimal small changes in the yield y. If you now want to look at a relatively small but not infinitesimally small change in the yield, well then what we can do as an approximation, that's basically coming from a Taylor approximation, the percentage change in the bond price due to a small yield change is equal to that bond volatility, okay, where you use the derivative, multiplied by that small change in the yield. And I'm going to talk about the limitation of this formula if that change in the yield is not small enough, and we can talk about the approximation error. But before we do that, I want to turn to an example where we can illustrate how this concept of the bond price volatility is useful. And what we want to look at is something called duration-based hedging. So let's suppose you're a bank, you borrow at the short term and you lend at the long term. And for simplicity, we assume that your liability side is given by 1 year zero coupon bonds. And on your asset side, what you want to consider is investing in some 30-year zero coupon bonds. And whatever you don't invest in the 30-year zero coupon bonds, you use some other activity in the bank which is not exposed to interest rate risks. Let's suppose that the 1-year spot rate is 5% continuously compounded and the 30-year spot rate is 7% continuously compounded. Now the question is, how much money should you lend to minimize the exposure to small parallel shifts in the yield curve? And again, we assume that whatever money you do not lend in these 30-year bonds, that money is just not exposed to any interest rate shocks. At this point, I would encourage you to stop the video for a minute and try to write it down by yourself and try to figure out how much money should you actually lend in these 30-year bonds so that your balance sheet are immune to interest rate changes. So the first thing we have to know that the duration of zero coupon bonds is exactly equal to the time to maturity of the zero coupon bonds. So meaning that for our liability, for our borrowing, since this is done at 1 year zero coupon bonds, the duration of the liability is just going to be 1 year. On the other side, we invest in 30-year zero coupon bonds, meaning that the duration of the assets is going to be 30 years. Now, when we want to figure out by how much does our liability and our assets change as there is a shock in interest rates, then what we can do is we can use our formula from before where we say the change in the bond price is equal to minus the duration times the change in the yield of the bond, and then we bring this price of the bond on the other side. Okay, so that's what we have here. The change in the bond price is minus the duration times the yield times the current bond price. So what does this mean for our balance sheet? Let's denote V by the value of the assets which are exposed to interest rate risks, PA, minus the value of the liabilities which are exposed to interest rate risks. This is PL. And how big are PA and PL? Well, in our question, we say that you borrow $1 billion. So that's the value of your liability. And the value of the assets or this investment in the 30-year zero coupon bonds, that's exactly what we want to figure out. Now, the idea is we want to figure out by how much does this value of these assets and liabilities change as interest rates change. If interest rates drop, for example, that's actually good news for our 30-year zero coupon bonds. It makes our assets more valuable. But on the other side, if interest rates drop, then also our liabilities are actually more valuable, and that's actually bad news on our balance sheet. Plugging in for these changes in PA and PL, we have minus the duration of our assets times the value of our assets times the change in the yield, and then minus that change in the liabilities minus the duration of the liabilities times the value of the liabilities times the change in the yield. Now, since we assume that we have parallel shifts in the yield curve, so meaning that if this was our current yield curve, we consider a parallel shift in the entire yield curve to this new red line, either up, or a parallel shift downwards to this new red line down here. But the key assumption is that basically the change in the 1-year spot rate is exactly the same as the change in the 30-year spot rate. So in that sense, these delta Y, these changes in the yields of the assets and the changes in the yields of the liabilities are assumed to be exactly the same. So in that case, we can factor out delta y, this change in the yield, and what we are left is just the duration of the liabilities times the value of liabilities minus the duration of the assets times the value of the assets, and this entire thing multiplied by the change in that yield, delta y. Now, what is again the purpose of our question? It says, how much should we lend in the 30-year zero coupon bond, so on the asset side, to minimize our interest rate risk? This condition means that we want to set this term inside parentheses equal to 0, which means that PA should be exactly equal to the duration of liabilities times the value of liabilities divided by the duration of the assets. So that's what I write over here. Now let's plug in all these values. So the value of the liabilities is $1 billion. Then the duration of liabilities is 1 year. Duration of asset is 30 years. So that means we should lend in these 30-year zero coupon bonds 1/30 of $1 billion, or which is equal to $33 million. If we do that, that means that a small increase in the entire yield curve, so a positive parallel shift or a negative parallel shift, will exactly affect assets by the same amount as it affects the liability side, and therefore our entire balance sheet is risk neutral. So we don't gain or lose money if there is a parallel shift in the yield curve. This duration-based hedging concept relies on some assumptions. The first one is that we only have parallel shifts in the yield curve. Now, let's suppose that instead of having the red line, we could also get something like the blue line here, where the 1-year spot rate change might be different than the 30-year spot rate change. Well, in this case, we cannot write the change in the value equal to this formula over here, because that yield change for the assets and the yield change for the liability are not the same anymore, and we cannot factor out delta y. So then we will not end up anymore with this same duration-based hedging formula. Or in other words, if we would follow this hedging strategy, it wouldn't be perfect anymore. The second shortcoming is liquidity risk. Liquidity risk means that in our example, we assume that we can, for a 30-year time horizon, always roll over our borrowing. So that means we can always keep borrowing again at a 1-year horizon. Now, this may not be true during a crisis. For example, during the 2008-2009 global financial crisis, some institutions were just not able to borrow anymore. And the final issue is the assumption about small changes in the yield. And this goes back to our approximation assumption that the change in the bond price is well approximated by this first order Taylor approximation. Let me go back again to this figure where we showed how the bond price depends on the yield of the bond, where we said that if the yield is bigger, there's more discounting of the face value, and therefore the bond price is smaller. And in this figure, what does this first order Taylor approximation say? So we say that the change in the bond price is approximated by the first derivative of the bond price with respect to y times delta y. This approximation says that if you are at point y1, then you move along a linear line which is a tangent to the curved line exactly at that point where the yield is y1. So that means your approximation says that if the yield increases from y1 to y2, then the bond price drops from this value over here all the way down to this value down here. Now, clearly, if you plug in directly into the formula of discounting the face value, then the actual bond price should be up here. Notice that this error can be quite large if the change in the yield, this delta y, is large. But this approximation error is very tiny if delta y was just a very small number. So therefore, what we say is that our approximation here is good as long as delta y is small enough. Now, how do you deal with these shortcomings? So let me start with larger changes in the yield. Well, this is quite simple. Instead of doing just a first order Taylor approximation, I also add a second order or maybe even higher order approximation terms. And in particular, the second order approximation, where you take the second derivative of your function, that's what we call the bond convexity. And in that case, then the percentage change in the bond price will be minus the duration times the change in the yield plus 1/2 that convexity of the bond times the change in the yield square. And of course, you could now add also third order, fourth order, and higher order approximations. But in general, interest rate changes are just a few percentage points, and a few percentage points to the power of 2 is already a quite small number. So then power of 3 or power of 4 is really very close to 0. If you are not happy with just the duration-based approximation of the bond price change, then taking into account the bond convexity, that should be good enough. Why is it called convexity? Basically because the second order term starts to take into account the curvature of this curve. The second problem of taking into account non-parallel shifts in the yield curve is a little bit more complicated. And there are really two different methods how you can deal with that. The first method would say, well, maybe it's a better idea to slice up your yield curve in different buckets. And we assume that within each bucket, the yield curve change is parallel. So indeed, if I'm going from the black line to the blue line up here, that thing is pretty much parallel. Moreover, in that second bucket, if I look from here to here, that thing might be close enough to parallel. Then looking at that third bucket, again going from here to here, that thing can be also close to parallel. Now it's true that if I compare this change to this change, they are very different, but the change over here to the change over here is quite similar, and the change over here to the change over here is quite similar. So now instead of doing a duration-based hedge for the entire portfolio which I have, I would say that I look at my assets with durations within that bucket, and I do a duration-based hedge with my liabilities within that bucket. And separately, I look at my assets and my liabilities with durations within this bucket to do a duration-based hedge. And I look at my assets and my liabilities within these buckets of durations and do another duration-based hedge. Now, of course, in our simple example where we only have liability with 1 year duration and another liability with 30-year duration, there you cannot do that. But in general, if you think about the bank, there are many assets and you can do duration-based hedging within each segment. Now we are going to look at forward rate agreements, which are interest rate derivatives that allow you to lock in an interest rate at a future point in time for a specific time horizon. And we call these locked-in interest rates forward rates. And we denote them by F with the subscript small t. That's when you sign that forward rate agreement to lock in the interest rate in the future. And then in the superscript, you have T1 and T2, which define that future time horizon from when until what time you're going to lock in an interest rate. Now, to show you exactly how this works with forward rates, I want to draw a timeline, and today we are at time small t, and then we have seen before, if you go to, let's say, a bank and you want to borrow or lend money from time small t to time t1, then the bank may give you some spot rate of r small t t1% per year, and let's suppose this is in continuous compounding. Now you can also ask the bank, what if you invest from small t to time t2, and then they give you a different interest rate. It's going to be the spot rate or t2. And how about now you ask that bank, what kind of interest rate can I lock in from time t1 to t2? And then that bank would tell you, we can give you the forward rate F, which again, you lock in at time small t, and then that rate applies for the time horizon between t1 and t2. Now, how do we determine that forward rate F? Well, it turns out there's a very simple no-arbitrage argument. Let's suppose you have $1 today and you want to invest that dollar until time t2. Now, there are two ways to do that. The first way would be you just take your dollar and you invest it from time small t to time t2 at just the spot rate RT2. So that means, since this is in continuous compounding, $1 grows to e to the power of that spot rate between time t and t2 multiplied by the time horizon from small t to t2. Now there's the second way to invest that dollar. You could also bring it to a bank and invest it until time t1, and that you would do at the spot rate RT1. So that means, again, if it is in continuous compounding, $1 will grow to e to the power of RT1 times the time horizon between small t and t1. Now back at time small t, you already know how much money you're going to get at time t1 from that investment because it is a risk-free investment. So back at time t, you can already sign with a bank a contract that you're going to reinvest this amount of money from time t1 until time t2. And so the bank would offer you the forward rate for that reinvestment. And that means the amount of money which you receive at time t2 is the amount of money which you have invested at time t1 multiplied by the gross return which you get from the forward rate agreement. So you earn this forward rate F, which is locked in back at time t for the investment between t1 and t2. And again, we have to multiply that by the time horizon between t1 and t2. Now notice that you already know back at time t how much you will get at time t2. So this is a risk-free investment. So therefore, both of these methods have an investment of $1, and I know exactly how much cash flow I receive at time t2. And therefore, these investments are both risk-free and they're both equivalent, and therefore, they both have to give the same return. So that means both of them have to be equal. And that's exactly our no-arbitrage condition to pin down the forward rate F. So you have that spot rate for the longer time horizon times that time horizon from t to t2 is equal to the spot rate from t to t1 times that time horizon from t to t1 plus the forward rate which you lock in back at time small t for the time horizon t1 to t2 multiplied by that time horizon from t1 to t2. Or then solving for F, the forward rate, that's just going to be equal to the spot rate again from t to t2 times the time horizon minus the spot rate from t to t1 times the time horizon divided by the time horizon between t1 and t2. Let's look at how we can make money if this equation doesn't hold. If the forward rate is smaller, then we see that investing $1 from small t to time t2 at that longer spot rate yields a higher dollar amount than if we invested through these two steps at the shorter spot rate and the forward rate. That means the arbitrage strategy would be borrow $1 through this two-step procedure and invest that dollar at the higher return. So what does that mean? It means that you borrow $1 from small t to t1, and that means you receive at time t1 $1, and you have to pay back e to the power of r small t to t1 times t1 minus t dollars at time t1. Now you also sign a forward rate agreement that you borrow this amount of money from t1 to t2. This means you receive at time t1 e to the power of r t1 times t1 minus t dollars. And at time t2, you have a negative cash flow equal to this amount. And then finally, we lend at time small t $1, so you have minus $1 here, and we receive at time t2 this amount of dollars. So let's look at the overall cash flows. Let me write it up here. So we receive $1 from borrowing, we have to pay $1 from lending, so that means $0 today. So how about at T1? So I borrow through the forward rate agreement exactly an amount of money which I have to pay back from that initial dollar which I borrowed at time small t. So that means again equal to $0 cash flow. And at time t2, here I have clearly a positive cash flow because this amount which I receive from lending the $1 is larger than this amount which I have to pay back because I have borrowed through the forward rate agreement. And again, this is positive exactly because the forward rate is too small. Finally, we can turn to the question, what if the forward rate is larger than the no arbitrage expression? In this case, we just do the opposite of what we did before. That means we lend $1 from t to t1. That means initially we have here minus $1 at time t, and then we receive e to the power of small t to t1 times t1 minus t dollars at time t1. And we sign a forward rate agreement to lend that amount of money, which I know that I receive at time t1, from t1 to t2 at the forward rate. That means through that forward rate agreement, then at time t1, I have to pay exactly this amount of money, which I have earned at time t1. And that means I receive in the future that promised amount over here. And then on the other side, we borrow $1 from time small t to t2. That means initially I get $1 and I have to repay this amount over here. Now again, at time small t, I receive $1 from borrowing. I have to pay $1 from lending. That means zero cash flow at time small t. At time t1, well, here I receive money because I did lend $1 at time small t. But then I signed a forward rate agreement that I lend this amount of money until time t2 at the forward rate. And so again, this adds up to zero cash flow. And then at time t2, I'm promised to receive this amount of money, which is larger than what I have to pay back from borrowing the $1 from small t to t2. Again, why is this larger over here? Because the forward rate is too large. So again, we have here an arbitrage where I get for sure some money at time t2. The only way to have no arbitrage is if the forward rate is exactly equal to this expression. Now let's go back to the lecture notes and we see exactly this formula over here for continuously compounded returns, where the forward rate is just an expression depending on the spot rates from small t to t2 and small t to t1. Now we can use the exact same no arbitrage argument also for different compounding frequencies. And over here I provide one formula with m times compounded rates per year. The argument is exactly the same. We just compare two investment strategies. One's where you invest from small t to time t2 and you earn the spot rate RT t2. And the other strategy is you invest from t to t1 at the spot rate RT t1 and then reinvest at the forward rate F between t1 and t2. Of course, you could also mix up different compounding frequencies where you have, for example, m times compounding for one rate, continuous compounding for a second rate, and let's say some n times compounding for the third rate. And in some sense, you can just use either of these formulas which I have on the lecture note and just plug in equivalent rates with different types of compounding. That would be exactly what you get if you mix up compounding frequencies. Or you could go back to what I just did on the virtual whiteboard and just work directly with different compounding frequencies to derive a new formula. So as I said before, to lock in forward rates, we use forward rate agreements. So in a forward rate agreement, you have one lender and one borrower, and they agree to borrow and lend some principal amount L at time t1 until to t2 at the interest rate given by this forward rate F. The convention in the real world is typically that F is at a compounding frequency m equal to 1 divided by the time horizon between t1 and t2. So the idea is that you have exactly 1 times compounding over that entire time horizon. Moreover, in reality, instead of actually lending and borrowing the principal L at time t1 until time t2, what lender and borrower in the forward rate agreement do is they will observe the actual spot rate at time t1 for an investment until time t2, and then they will just cash settle. So meaning that you would try to figure out which position actually has a positive value and which has a negative value, given the forward rate which you have locked in back at time small t, and given now how high the interest rate between T1 and T2 is in the market. So let's look at the lender in the forward rate agreement and what is the payoff at time T1. So the lender is supposed to give L dollars to the counterparty. So that's what we have here, L times -1. On the other side, the lender is supposed to receive on that L dollars this much interest at time T2, which is just determined by the forward rate F. Now, because that payoff is at time T2, to figure out what is the value of it back at time T1, I just discount this entire payoff by the current spot rate between time T1 and T2. Notice that here I write the forward rate in M times compounding, where I assume here that that spot rate between T1 and T2 is in continuous compounding. So if this expression is now positive, that means the lender in the forward rate agreement will receive some cash from the borrower in the forward rate agreement at time T1. Notice that the payoff to the borrower is exactly the opposite of the payoff of the lender, so it's a zero-sum game. Now, what about the lender's value of the forward rate agreement at some point S before time T1 and after he has signed the forward rate agreement at time T? Well, we can do exactly the same as before. Again, the lender is supposed to give L dollars to the borrower at time T1, and the present value of that is now just by discounting from time T1 back to time S at the prevalent spot rate, RS to T1. And then on the other side again, if he lends the L dollars, then at time T2, he's supposed to receive L times that fixed interest at the forward rate F. And again, we can discount that from T2 back to time S using that spot rate in the market, RS to T2. Notice that this formula actually also nests the payoff at time T1. In that sense, you can just replace S by T1, and you see exactly that this formula is going to be this formula over here. In practice, we see that a lot of institutions, and not only financial institutions, but also other corporations, they take positions in forward rate agreements. And the idea is that these corporations want to hedge unexpected shocks to the interest rate. Forward rate agreements exist on all major currencies in the world. And the forward rate agreement market is actually quite liquid. So meaning that bid-ask spreads are very small. They're typically just about 3 to 4 basis points, where a basis point is 0.01%. Notice that forward rate agreements are only traded over the counter and they are not available on exchanges. So that means if you are a corporation, you want to enter a forward rate agreement, what you would do is typically you would find your partner bank and you would just make this agreement with that bank. Notice that there are also other ways to hedge interest rate shocks. And for example, we could use treasury bond futures, we could use euro-dollar futures, or other types of interest rate derivatives. And we're going to talk about some of these interest rate derivatives in chapter 5. Notice we can also rewrite the formula for the forward rate in these following two ways. The nice thing about this is that if we see an upward sloping yield curve, so meaning that the longer spot rate is higher than the shorter spot rate, then we see immediately from this formula over here that this term is positive, and therefore the forward rate is larger than the bigger of the two spot rates. And this makes a lot of sense, since if the longer spot rate is larger than the shorter spot rate, well, then you need an even larger forward rate to compensate, to make these two investments of the $1 from time t to t2 equivalent. Moreover, if the yield curve is downward sloping and the longer spot rate is smaller than the shorter spot rate, then again from this formula over here we see now that this term is negative, and then therefore the forward rate is even smaller than that longer spot rate. Again, this makes sense by the same argument as before. If r t to t2 is smaller than r t to t1, well, then this thing has to be even smaller to even out these two investments of $1 from time t to time t2. Finally, if the yield curve is flat, meaning all the spot rates are equal, well, then we also know that the forward rate is equal to the spot rates, because this term over here is always 0. On slides 27 to 31, I have exactly the derivation of the forward rate as what I did on the virtual whiteboard. Then just some final remarks about forward rate. So notice that the forward rate was fully determined by a no arbitrage argument, and we only need to know the current spot rate. Okay, the spot rate from time t to t1 and the spot rate from time t to t2. And we don't need to know anything about what we expect to happen to interest rates at the future point in time. So everything is just given by the current term structure of interest rates. Here I just go back to that table where I have an illustration of different spot rates, and just for some example, and of course it's not an exhaustive list, I do derive a few different forward rates. So this one is the forward rate which applies between starting in 6 months until the end of the first year. So that would be just implied by the 6-month spot rate and the 1-year spot rate. Then, for example, the second over here, that's the forward rate between starting in 1 year and year 2, and that's implied by the 1-year spot rate and the 2-year spot rate, and so forth. So let's look at one example. Suppose you work for a bank and you see that the 1-year spot rate is 5% right now in continuous compounding. And then the research team in your bank says that, well, we expect interest rates to increase after 1 year. And the best estimate which we can get from some macroeconomic models is that the 1-year spot rate in 1 year time is going to go up to 10%. Of course, this is just an estimate, so it's just the expectation formed by the model of this research group, and there is some uncertainty. So maybe the spot rate is going to be even higher, maybe the spot rate is going to be lower. Now, suppose that you see in the market that the forward rate which you can lock in today to either lend or borrow in 1 year for 1 other year is 7%. Now, suppose that the yield curve is flat, so meaning that 2-year spot rate, 3-year spot rate, and so forth today are all equal to 5%, so equal to the 1-year spot rate. The question is there an arbitrage opportunity? So what we do is we look at our formula. By no arbitrage, the forward rate is supposed to be equal to the spot rate from today over the next 2 years times the time horizon of 2 years minus the spot rate from today until the end of the first year times 1 year, which I omit, divided by that investment horizon starting in 1 year for 1 more year. Okay, and if you plug in these numbers, that gives you 5%, which is actually what we have seen before, where we said, well, if the yield curve is flat, if all the spot rates are the same, then the forward rate is also equal to the current spot rates, okay, which is this 5% over here. Now notice that we actually have in the market a forward rate which is 7%, so meaning the forward rate is actually larger than what it should be by the no arbitrage argument. So again, how do you make money? Well, if the forward rate is too high, then the attractive thing to do is to lend at the forward rate. So that means what we would do is we borrow $1 today for 2 years at 5% spot rate. We take that dollar, we invest it for 1 year at the 5% spot rate, and then also today at time 0, we sign a forward rate agreement where we promise to lend e to the power of $0.05. Where does this come from? Well, this comes from the fact that we know that $1 lent at time 0 until time year 1 will actually yield this much money. So I signed a forward rate agreement to lend this much money in 1 year for 1 more year at this now too high forward rate of 7%. So what does this mean? Initial cash flow today is, well, the dollar which I borrowed, I also lend it, so I get 0 cash flow today. In 1 year, I get this amount of money from the $1 which I have lent for 1 year. But then again, this amount of money I have to already pay again through the forward rate agreement. So that means again 0 cash flow. And then at the end of year 2, the amount of money which I get is, well, this amount of money which was reinvested at 7%. That means I get e to the power of 12% dollars in year 2. And then on the other side, from the $1 which I have borrowed initially, I have to pay back that $1 plus interest, and that's invested at 5%. So I have e to the power of 5% times 2, or e to the power of 10%. Clearly, this thing is positive, and therefore I have an arbitrage profit. Now, what if the yield curve was not flat, and in fact it was increasing, and the 2-year spot rate is 6%? Again, plugging into my formula, by no arbitrage, the forward rate should be equal to this thing over here, which now I have 6% times 2, so 12% minus 5%, that's 7% divided by 1, and that's exactly the forward rate which I have in the market, and therefore there is no arbitrage opportunity. Finally, I just want to talk a little bit about theories of term structures. The first popular theory is the expectation theory, and that tells you that the forward rate is actually equal to the future expected spot rate. And given the earlier argument, this means that an increasing term structure implies that the forward rate is higher than current spot rates, and then therefore the market expects the future spot rates to be higher than today. Or in other words, the market expects that interest rates are going to increase in the future. On the other hand, a decreasing yield curve implies that the forward rate is smaller than the current spot rates, and therefore the market expects that interest rates are going to decrease in the future. Notice that most of the time in reality, the yield curve is in fact increasing, and therefore the expectation hypothesis would say that most of the time the market thinks that interest rates are going to be higher in the future. Now, this is clearly not the case, as interest rates are stationary and they're not most of the time increasing, and therefore the expectation theory cannot explain the data all that well. Moreover, there are many academic papers which actually show empirical tests which show that the expectation theories have some flaws. In addition, the expectation theory may also struggle to explain term structures which are not either just strictly increasing or decreasing. For example, in reality, we sometimes observe hump-shaped yield curves. In contrast, the market segmentation theory doesn't really tell us about what market participants expect to happen to interest rates in the future. But this theory tells us that there are different investors trading bonds with different maturities. So you can think of it as the following. I am in my mid-30s, and if I consider an investment problem to save for my retirement when I'm 65, then for me a risk-free asset might be something like a 30-year bond. While for my father, who is just about to retire now, the risk-free asset may be very different. Therefore, my demand, if I'm looking for a risk-free asset for my retirement savings, will be trading in a much longer maturity bond than what my father does. And since there is a segmentation for different maturity bonds, and demand and supply can be somewhat independent between the different markets, the term structure of interest rate really can take any shape which you like. Finally, the liquidity preference theory tells you that investors don't want to tie their money for too long time. Let's suppose that someone wants to invest for 5 years. The liquidity preference theory would say this person doesn't want to give the bank his money today for 5 years and not have the opportunity to withdraw it again. That person rather has it in a short-term investment, let's say always on an annual basis, and be able to withdraw the money before the 5 years in case he suddenly has some big expenditure. Therefore, if someone commits to leave the money in a bank account for a longer time horizon, this person wants to be compensated with a higher interest rate for not being able to withdraw the money early. Okay, in that sense, the liquidity preference theory would always predict that spot rates with longer maturities have higher interest rates, and therefore the yield curve is upward sloping. Now, in reality, it's probably true that none of these theories by itself is a true explanation, but probably it's some combination of them together. And this concludes chapter 2 about interest rates and forward rates.